And so it's a fantastic event today, and great to have you here, Gregory, to present on your work. And so we had earlier a colleague of mine presenting about Ocado. She's working there at Ocado now. And so that is a larger enterprise, of course. And I would say, Greg, you are more the entrepreneur and the startup kind of person. So really, really interesting now to hear your perspective. And indeed, I'm looking forward to your presentation. So maybe you want to share your screen now, and we can get started. And maybe just before we start, again, a reminder to everyone. So if you cannot hear anything, or if there are problems with the connection, please, raise your hand with the raise your hand icon, and we'll see whether we can improve the situation. But otherwise, it's all yours, Greg. Thanks again for coming and presenting.
Yeah, no problem. Well, hi, everyone. Really great to be presenting to you all. And shame I can't see you in person in the lecture theatre. But I have been to the lecture theatre, or some of the lecture theatres in QMUL, so I can imagine what it'll be like being there. So, and you can imagine what it'll be like me being there. So yeah, I'm going to give you a presentation about Dogbot, which you can see on your screens now, I expect. And this is a quadruped robot in development at React Robotics over the last 3 years. And I'll give you a sort of brief overview of why we're doing this, who's been sharing in using this platform for their research. I'm going to look at how we built this as well. So I think it's quite interesting for you guys just to see what it takes to build something like this, and to show that should be in reach for everybody. And at the end, a few comments on how about bringing this to market. So yeah, and currently the current status of this is that we've got to a point where we've got to this prototype, we've open sourced it. We're in a bit of a lull while we look for more funding to take it further, and obviously a bit of a lull with the coronavirus as well, so gives us time to just discuss that with various people. Okay, well, let's see if this really works. We'll start off with the first and let's see. You should. Hopefully you'll get a nice video. So this was recently in the Imperial Robotics Machine Intelligence Lab with Dr. Petar Kormashev. You can see in the background there's another robot, which is his robot. And it's just a quick view just to show what the robot's capable of. It's hanging from a gantry there, but it's not actually using that. It's just sort of just in case. And the reason we've done this is we wanted to build what it says here. It's our vision, really, a robot anywhere you go to do any task. And I think long term, this type of robot, it's a quadruped, it's the closest we could get to the type of robot that has similar capabilities to a human. In the leg locomotion means it can go to the same places we can go. And as opposed to a wheeled robot, which might struggle with steps, gaps, and obstacles. This is closer to what a human can do. And obviously, much longer term, we expect something that is much closer to the human form factor. So human really would be required to fulfill that vision. And something like this robot, you could imagine, once you've seen this presentation, I'm sure you can see it could be quite easy to evolve towards that form factor. But this is a good place to start, given that 4 legs is more stable than 2. So our approach to that really is to try and be the platform that brings together research and enterprise. And we started on the left-hand side with a platform business. It's sort of chicken and egg problem. Where do you start? And we've really started with researchers. So allowing them to use this platform and create skills and capabilities for the robot. So we provide the infrastructure and allow people to build on top of that. And in order to sort of transition into the enterprise solutions, then people who are used to using autonomous machines, drone operator 3D scanning, could actually then take this as a sort of ground-based drone and do 3D scanning of construction sites, inspection in oil and gas, and these are industries that we've spent time discussing how that could work, building up partnerships to allow us to transition into that. But right now we're continuing with this. In this presentation, I'll just talk about the research side of this. So yeah, here's something you might imagine research community wanting to do. This image was generated when we were discussing how we could enter sites that are participating in nuclear decommissioning. So these very unstructured environments, and there's a lot of interest in how legged robots would enable the transport of sensors over rough terrain, particularly in a place like in nuclear decommissioning where you have you may not have been into that particular room for 30 years, and there's no record of what's in there. And typically it looks like this. People, I mean, this is not a nuclear power station. There's, you know, Coke bottles in there, but there will be just tools, and everything has to be left inside, because if you bring it out, you've got to box it up and dispose of it. On the enterprise side, before I go into the detail of research, you can see here we have a Faro 3D scanner. I'll show you some videos of this in use later, but it's simple to add sensors to this. So payloads could be goods, so you could be delivering goods, you could be carrying sensors such as this, or you could be carrying tools, so robot arms with grippers, etc., to carry out other tasks. So let's talk about how we've been engaging with the research community. What you can see here is the URDF file, which you can use to run simulations in ROS and other physics simulators. I did mention that we gave a robot to Imperial College. That's actually in Petar Kormashev's lab. But other people, we've just given the URDF and had a look to see what they can do. So Antoine Cully has recently opened a lab at Imperial as well, and he's done some really interesting work looking at how robots adapt to injury, let's call it. So he'll deliberately configure a robot to restrict certain axes, and then that robot has to, in simulation, explore the potential solution spaces for reaching a goal, and that goal is to get from A to B as fast as possible, typically. And he can very quickly get robots to find novel locomotion patterns and regain some mobility. Now, when running Dogbot through those algorithms in simulation, he was able to get. Now, there's been no restrictions applied to Dogbot, but with the parameters that we provided in the URDF, he was able to get that to walk and generate its own walking pattern. Let's look at the video. Hopefully you can see that. He was able to generate that walking pattern, and I think he said it sort of took him about 45 seconds to get that to think of this walking pattern, which is a pretty logical walking pattern, so that's pretty impressive. This is Petar's lab at Imperial, so they just had this running in Gazebo, getting it to turn around. They also had this running the Xbox controller here, doing rotating. This is quite heavily supported. This is a previous version of the robot, which is has much smaller motors. so they just need to keep that stable. But they managed to get all the sort of necessary movements, the sideways movement here, running. And then also this was running in the construct, which is a virtualized version of ROS. Get that running. So we can go to they're creating tutorials, which is pretty exciting, because it's useful to be able to get up to speed on this quickly. And they just took our UADF and simple walking code we provided.
I would like to have it, the light purpley bluish bedside table of Dominic. If he gives it.
Can you this one?
Or that one, or both.
You want this or the other? I want this one.
Both.
Both. Or you can have this there.
Cool. So gives you an idea of how they're running that. So let's have a look at actually how we built this. Now we started off on the left here. Version 1 is like super simple. So all of the white parts are 3D. Spars are off-the-shelf carbon fiber. And then the motors are from their sort of DC brushless motors that you typically see in drones. So obviously they've had the cost, the weight, and the power heavily optimized for flight. So it needs to be really lightweight, high power density, and they're in mass production, so they're low cost. And then we had a custom controller, and then batteries. LiPo batteries from drones as well. This one's I'd say completely modular. So each joint has the same gearbox, motor, actuator design. On the right-hand side, we started to then actually get a bit more focused on stiffening up the frame and designing specifically for each leg rather than per motor. The legs are reasonably symmetrical. And you can see the key thing about this design is that the knee and shoulder motors for shoulder for pitch they're both at the shoulder, so they're not. So the knee motor is being activated, and in these two designs with the push rod. But the point is to keep the weight away from the knee, because you have to move the knee. So if you have a big heavy weight, if you're familiar with the animal robot, they have a knee in the motor, so they actually have to move the gearbox, the motor assembly, and it's pretty heavy. So their robot therefore is very slow. So compared to the earlier one, I mean, this is another sort of a small iteration. There are a lot of iterations. So if you go into our sort of repos for CAD, there's hundreds of iterations on the CAD. This is getting it walking for the first time on a lead, as you can see. So we can run this off a power supply, but in our office, power supply is not enough. We have to use the batteries to get sufficient current. And this walk was just simply this was programmed and then run in our own physics simulator, just to try and predict, just to evolve slightly how this should walk on what we thought the physics might be. And obviously a long-term goal, a lot of the AI research is to then try and then take data from the real robot and use that to feed back into the simulation, so we can more accurately understand what that simulation should look like. And other techniques like domain randomization, which you might have seen have been very successful, which is a sort of sim to real approach. And those are some of the approaches we're interested in pursuing. At this point, we gave one to Imperial College. This is their researcher, David Jedkin. He went on to work at Ocado in their robotics department, working on similar projects. So that's quite exciting for him to do his master's and then go on to that.
Oh my, Jesus.
So this robot was complex. Each iteration of the robot got shorter in terms of version-wise. So this is version 2, and I think the first one was something like a year. This one was maybe 2 years even working on the first one, and this one went down to something like down to a year, and the next one down to 6 months. So they sort of halved, but we're also reducing complexity by like 10x. So you can see the amount of chassis components here, and on the front faces here is where your shoulder is fixed, but there's just so many components here, and this is the component that fixes to it. You can see into the gearbox. I'll show you some actual images of the gearbox as well. You can see the sort of aesthetic on the controller housing here is sort of, I was looking at Star Wars spaceships and sort of getting a feel for what they look like, and then designing this afterwards, because part of designing robots is to make them look nice as well. And a lot of this is like completely optimized for 3D printing. So this is 3D printable. You can see some of the angles in here, which you can imagine we print on this flat face, and we're printing upwards towards this, so you can't have any overhangs. So everything is designed for manufacture and assembly. There is a split line on here, so this outer area was in this iteration designed to be 3D printed in rubber, but we found that not very reliable, so we actually built a skin and then in-molded that in the skin and ripped the skin off afterward. So there's lots. You saw how difficult that chassis was in the previous version. This is the current version, and you can see we now have an exoskeleton. So rather than an internal endoskeleton, we have this monocoque shell, which is very stiff. So in a beam, all the forces are at the outside. So in a tube is kind of the optimum shape for a multi-directional beam. And this is what we've built here. So this is a tube, but all the forces are at the outside. It's a thin 1.2 mil, sometimes 2 mil wall thickness in the main body there, and it's stiff. It's very stiff. This design, we changed the architecture so you can actually get full articulation, and the design of the body is really there so there's no interference with the range of motion. So this is not a choice about the aesthetics of the body being this lozenge shape. This is purely so that there's no interference with the legs when they go over or under when in the yaw range. So we changed a few things. We went up to EtherCAT, bigger motors, faster communication. We wanted to reach 1 megahertz for communication. We changed the push rods to these belt drives you can see here. Things like the battery casing are all integrated. So we really wanted to make this a little bit more like the professional robot that we'd want to deliver, and things like the belt are driven by wanting to have to carry the load. So this is specified. It's a 20 kilo robot. It's specified to take a 20 kilo payload. So if you divide that between each leg, that's nice. That's 10 kilos per leg when loaded, but realistically you're trotting, so actually when you're trotting, that's across 2 legs, so it's 20 kilos per leg. But if you're going down a flight of stairs, then you have all the load on a single leg, so you've actually got 40 kilos on a single leg. So you take into account that there's a lot of leverage on the belts. So they take something like 1,000 kilo through the belt. it's a lot. So quick demos here. If you're building a robot, just test it a lot. It's a good idea. Sounds good, because we have a helical gear in here, so it's really nice, really smooth compared to straight cut gears, which are bang against each other. And so these very rough and ready test rigs. Again, if you're building robots, like, it doesn't matter what it looks like when you're testing it. It matters that you find out what you need to know and get on to the next thing as fast as possible. Worry about aesthetics later. So on this robot, each motor has a potentiometer here. So what we wanted to know is the position of the motor relative to the position of the leg. So as we run through the gearbox, there are losses. So we want to find out about that. Let's see. So you can see in the bottom left here, there's a box. There's inside the leg, there's also another board which has an IMU in it. So we can detect the position of the leg, upper leg, relative to the body, and we use that for calibration. And the lower, we simply just measure the position of the knee joint and the motor. So you can see the motors here. These are, we've been buying off Hobby King. Turns out the Cheetah Mini is using these, and I'm sure lots of other people as well. We started buying them in China because it's cheaper, but there's so many of them out there. And this is the 3D printed drive motor, which running through a 1:21 gearbox means there's not that much force on it. But yeah, plastic does break, so realistically a metal gearbox is a requirement, and 7075 aluminium is about what's required. Or we can miniaturize that and put steel gears in there. You can see in here this helical gearbox. So what you just saw plugs into the top above this bearing. And this is the other side of the gearbox. And everything's 3D printed. So ball bearings are glass in this for weight reduction. So it's critical we kept below that 20 kilo weight just to make this thing agile, and that's basically industry-leading weight. So we built our own board. Charles hand soldered the whole thing, which is pretty damn hard, I think. And a lot of this is built there. You can see the capacitors there just to deal with the current surges. So there's quite a lot of sudden movements with locomotion. So really need to take up the slack so we don't burn out the board. So here's a quick video of what we were doing. We would be creating simulations and then using that to drive the robot. So finally, this is in an industrial scenario, in a construction site, walking very slowly just to stabilize the sensor. The sensor is a 30,000 pound 3D scanner, so we had to be a bit careful, but it's mapping the construction site. And what they can do with that data then is to compare that to the CAD model of the construction site to understand the difference between where they expect they've got to and the actual progress. Going through that process of getting a robot from very early ideas through to something that we could present commercially was obviously very difficult. We were running a consultancy at the same time to pay for that. We had a grant as well, which was reasonably well aligned with that. But at some point, we actually have to start getting customers to fund that. And if you can get customers, you can get some investment as well. So our sort of interim step there was to work with Lenovo, who sponsored our visit to Autodesk University, which is a big software conference with 10,000 people in Las Vegas, November. We put this out. We were on the big screen before all the big presentations, talking about the robot. And if you go online, you'll find their videos with us chatting away. But this sort of thing is sort of a step towards getting credibility for what we're doing, and helps people discover us, because it's important that we get funding, we get people helping out. And now that this is open source, it also gets the message out there that people can participate in this project. And obviously they built a really nice stand, so it makes our robot look amazing. Boston Dynamics had Spot Mini there as well. So a lot of what was happening was people would go, "Oh, I've seen your robot. It's amazing. Like, can I buy one?" And we're like, "Sure, yeah." And most people didn't realize there was more than one robot in the world. It's not just Boston Dynamics. But people who knew the difference. Some of the things that really helped this robot stand out, obviously the fact that this is 3D printable, meaning that you can maintain this robot. So if you've used drones before, you're pretty used to crashing a drone and fixing it. And this robot is something that falls into that sort of category. Like, you can fix this if you fall down a flight of stairs and snap something. And the fact that it's open source is positive. We think that's for a robot going forward. Right now, it's not a problem with AI taking over the world, but going forward, it's that idea that the robot's accountable and that the software has been shared and is open and people understand what's going on is an important sentiment. And obviously, the other one is cost. So rather than being something that's 100,000 or £250,000, this is something that we can sell for £20,000 to £50,000, or you can build your own, and that gets a bit more exciting. Then, if you've got a 3D printer and a spare 700 hours, you can print one. So, final goodbye from Las Vegas. Good message for today, when we're all kind of stuck indoors and suffering. We need a bit of love. And that's kind of it, really. All the details you need to contact me, are there. There's my email. This is Twitter. There's a YouTube channel. And if you want to download anything, go to GitHub, either our React Robotics repository or Charles's repository for earlier projects. And you can see some of the progress that we went through if you look on Hackaday. And yeah, any other questions? I'll switch this off, and you're welcome to ask questions. It might be easier to, I suggest, type them in the chat window, and I'll go through them one by one. And if you want any further questions, technical questions, you can either ask me, or I can, I'll CC Charles, and we can get back to you. And if you want to build one, we can help you.
Fantastic. Thank you very much, Greg. Super presentation. And maybe first of all, I would like to ask the audience to raise their hands to indicate your applause for the super presentation. Okay. Thanks for that. Yep. Thanks a lot. Yeah, great. Thanks, Greg. Fantastic overview, and I like to see things from a more from an SME point of view, small manufacturing company, and also to see the more the technical side of things. So really to give an insight into the issues you have in building robots and making walking machines. So I think we have time for some questions. So if you want to either send your question via text box, or if you want to just open your microphone and let us hear your questions. Harish, okay.
Yeah, thanks a lot for the fantastic and insightful talk, and for candidly sharing your experience about design and development of this robot. So my question is, what are the main outlying challenges which for example, mainly in the terms of design and hardware development for this quadruped robots?
So if I heard that correctly, you're asking what are the main challenges. I mean, the main challenge is getting enough money to do it, because money gives you time and allows people to concentrate on working on the design. If we go down a few levels to sort of within the design itself, I mean, we were quite constrained because we decided to predominantly use 3D printing. That obviously opens up lots of benefits. So we can iterate very quickly. For instance, when we had the robots at Imperial, if something broke, they would call us up and say, this broke, send us a video on WhatsApp. We had a WhatsApp support line, so they'd just send videos of things that are broken, and then we would revise the CAD and go in, print that overnight and go in the next day and fit it. So you have all these sorts of benefits, but I mean, we're using PLA, which is probably the best performing of the plastics that you can use at low cost, but then sort of plastics that are 10 times the cost, and they will perform less. So then you need expensive machines. We're just using a Prusa, but you need a sort of 20,000 or 100,000 pound machine to take advantage of these better plastics. So, you know, I think while we were extremely agile, it sort of prevented us from maybe progressing as fast, because I mean, we basically had to design the solutions and optimize this, to optimize the designs rather than just relying on higher performance materials. So I think in the long term, that's good to be doing that. But yeah, you certainly need, this is quite a big project. And if you were to start from scratch with this, it will take you years. I think there are some precedents online of people 3D printing robot dogs, but so if you're going to build one, just start with the most advanced open source one you can get, basically, because it's a lot of work.
Yeah, thank you. Thanks, Harish, for the question. Any other question? So maybe I can ask. So I think you made fantastic progress, and I remember seeing your system, I think 2 years ago when you were at Queen Mary. That was for Taros. Well, it was last year actually, wasn't it?
Yeah. Well, I think we've been twice. So we came
and before, yes, yeah.
Yeah, we came with the older one and then with this one as well.
Yeah. So I think amazing progress over the years, and I think this version that you're showing there is even beyond what you showed at Queen Mary last year.
I think this one we had it last year, but the previous year, Aros, or maybe 2 years before that, we had the older robot, which was this sort of thinner carbon fiber, all this sort of complex framework. So this is a lot more homogeneous, much simpler, sort of instantly recognizable as a product rather than something that's been sort of assembled from separate pieces. So.
Okay. So my question is on the commercial side. I mean, you said already that your system is a lot cheaper than what we see at Boston Dynamics, maybe a factor 10 down in price.
Yeah.
But still, I suppose it is challenging to sell these and to keep the company going. If you're okay to give some comments on that.
Yeah, I mean, so to get to a point to sell these, they need to be extremely robust. So this is still a research project, and not yet to the point where people are buying them. There's still another iteration to go, really, which is to make this. I mean, we have a sort of. Our goal was to get this from lasting sort of hours to days to years, and we're still really on the hours stage because we're using these plastic gearboxes.
Yeah.
Other parts of the robot are lasting days. When I say days, I mean it doesn't break in a couple of days, but say the chassis of the robot, major plastic, there, but they won't last years, basically. So they're not into the years category yet. Things like the motors should be fine. Carbon fiber should be fine. So it varies across the robot. And yeah, so as I alluded to at the beginning of the conversation, we're sort of taking a bit of a break because we've spent much more than we said we would spend building this robot, but we got a bit carried away, to be honest, because it was good fun. We said we'd do a year, and then we did 2, and then we did 3. So, we went a bit further. And as this is funded by consultancy, if you're doing consultancy, you can't do the robot. So it's a bit difficult to do both. I think going forward, we're talking to strategic partners, and certainly if we can keep this moving internally, we will. And by open sourcing it, we hope that it will continue externally as well. And I think that's, at the moment, that's sort of as far as we can go. But if you're interested in creating a business like this, do move to America if you get the chance. You might find it a bit easier. The UK and European venture capital industry is quite risk averse with hardware, and if you've got customers for something, you'll find it a lot easier. But with something like this, there's quite a lot of research before we can even get to that point. So hence us working with the research departments in institutions, because they would typically build something like this themselves. So for them, having a robot that might break occasionally is normal, but not having to spend 2 years building it in the first place is an amazingly huge bonus. So this is like a big deal for Imperial, because Petar's lab builds robots, but getting the time to build something like this just wouldn't have happened. So the value, it depends who you're talking to. So there's lots of value in a robot that will break occasionally now for researchers, but for professionals, clearly in enterprise it's just not okay, because you're losing money. So the next step is get things like the gearbox, which is where most of the issues are, get that resolved. We have designs. We also have a design for an all metal CNC version of this, which obviously, because if you think about the design for manufacture, it varies because the production technique is different to 3D printing, so you can't do it quite the same. But the cost goes up again, so even more money needed there. So we just didn't want to get to a point where we were selling £100,000 robots, because we're trying to avoid that.
So, exactly.
Conversely, to end up with a robot that isn't £100,000 in the long term, if we want one at this then the solution is higher volume, and design for manufacture there, then moves to injection molding and other things. But hopefully there's enough that we can do. Hopefully we can get enough of these out for researchers if we get a chance to kind of get back into this project.
Yep, thanks for that. Maybe you saw the question.
Okay.
Yeah. So
the team is just. I'll read out the question for other people and for the recording. But what type of disciplines or backgrounds required for this type of projects, and how big is your team? So, there's 3 of us in the team. Myself, Charles Galambos, who's the CTO, and Nick Greenway, who's Chief Operating Officer, and both of them are engineers. Charles did his undergraduate degree in electronic engineering and went straight to PhD in computer vision at Surrey. Nick did mechanical engineering. He's a first from Cambridge. Nick actually went into power generation and then off into finance for 15 years because obviously he got lots of money from doing that. But he was building. He wasn't trading. He was building the software trading platforms, running large.
Maybe, Greg, maybe you can repeat the last sentence.
Object recognition and facial recognition. He ran that for 13 years, and basically at the end of that, when that was sold, or just before it was sold, the current wave of artificial intelligence using deep learning arrived, and basically in 3 months they were able to replicate their 12 years of research and beat their benchmarks. So he kind of realized there was an interesting future ahead, but his future that he decided at that point was not a future of static image recognition. It was about time-based understanding of the world, and that's what we have as humans. So he started an AI company. Prior to that, I've been doing robotics, working in the industrial robotics space. So I developed a sheet metal forming process where you could form something like a car body panel, but without the mold. So normally you need a mold to press metal into shape. And I developed a process that could take multiple industrial robots, lift up a sheet of metal and form it into curved shapes. So that was a 20-year project. I started when I was 17, ran a company for 10 years. During that time, spent consultancy doing developing other processes, so doing things like metal 3D printing with welding. We installed systems for people, developed software for that, for academics, for Fortune 500 companies. So kind of grew a bit. And then I realized that really a lot of people were asking us, why can't you do these simple processes in our factory that people do? And I sort of said, well, that's the simple ones that people do are actually the hard ones for robots. But that kind of got me thinking that, okay, perhaps the field of artificial intelligence is progressing fast enough. Perhaps machine learning can assist us actually learning these processes. And that's when I started working with Charles and Nick on that sort of joint mission to get human level intelligence operating. Initially, we thought factories and things, and we started investigating that. But there are many elements to sort of human level intelligence and common sense. But the main one really is embody that intelligence in something that can interact in the world in order to learn. And yeah, we started with a torso with hands, and we were sort of held back by sensors at that point. And we moved on to legs. And yeah, I don't have a mechatronics background. I have more of a design and innovation background, but I've always built things myself. So I'm in charge of building this robot. I do all the assembly and the design and the CAD, alongside Charles, who's doing CAD and electronics. So I think you guys are well placed in terms of experience, but you certainly need a team. It's important to have a varied team. Like in our team, there is overlap in roles between everybody. There's always two of us that can do something, and people, obviously, individuals have specialisms as well. So, yeah, my previous company, I started it and ran it predominantly on my own. I would definitely not recommend that. Just don't do it. Find people to help you. Like emotionally, you need that. You can't do it on your own, basically, and you can't make decisions on your own that are good. I will say that, like, categorically, you just can't. You need to discuss them. Even with one person, it'll help, but with 3 people, it helps a lot. You don't need much more than that, though.
Okay, no, that's a fantastic overview, and I think what I see there is, yes, you need some background. It could be engineering, but also design seems to be the right thing. But I also see that some practical skills, some feel for the matter is important. Yeah. And also what I can see is that the team is very important, as you very clearly said. So not to do it by yourself. I suppose in addition, and I think you mentioned that as well, a bit of a business sense, because I mean things work and other things maybe don't work so well. So I suppose a combination of these attributes, if one was interested to try out, could be something.
Yeah, I think I'd really recommend that your students do aspire towards living the capitalist dream, so to speak. I mean, there are other ways of being not too capitalist, like open sourcing your projects, but you still need to fund this. And there's a huge amount of infrastructure available to make sure that you're not sort of poking around in the dark when you start a company. There's so much resource there for startups, a lot of it coming out of Silicon Valley, on how to make sure you don't fail. So it is possible, I think, if you look at this intelligently, to be successful. You know, if you've got an idea and you feel like your research could go further than what you're doing now, like maybe do a PhD, maybe start doing the research, turning the research into reality immediately. But yeah, there's plenty of resources out there, so I think you should be all right.
Good, fantastic. Thank you very much. Maybe we can take the opportunity again to thank Greg by raising your hands. Thanks a lot. Yeah.
Thanks, guys. I really appreciate you taking the time to listen, and really appreciate the questions.
Thanks a lot.
Be in touch.
Yeah.